Welcome to MSP lecture series on main group chemistry. In my previous lecture, I was discussing about Wade's rules and how to use Wade's rules to elucidate the structures of boron hydride clusters, and I had mentioned about the type of clusters we have and all those things. Let me continue from where I had stopped. So, I will show you now how nido and arachno cages can be derived from the parent closo cage with n equals 6, that is having 6 vertices. For example, you consider octahedron having 6 vertices, and from this one if you remove one of the capping positions, okay, and it becomes nido. And once after removing one from capped, we should not make an attempt to remove another from cap. In that case, what happens, we will be left with 4 boron atoms in one plane. In that case, what happens, we know that each boron atom has a tetrahedral geometry, and arriving at tetrahedral geometry when they are in plane will be difficult. As a result, instead of removing to arrive at arachno structure, instead of removing the axial one, we have to take out one from the plane. Okay, and this is how it is. Okay, so remove one vertex from the plane, so that leads to the formation of arachno. So this rule we should follow. The first one, especially trigonal bipyramid, I had mentioned, the one that makes 3 connectivity is essentially this one. You can see here, this makes 3 connections. This should be taken out to make nido. Of course, from nido if you remove one more, it becomes trigonal planar. So, we do not have those kind of examples. So, nevertheless, one should remember first one has to be taken out from the capping positions or axial one, the next one should be preferably from the plane. Okay. So, you can see here I have given n plus 1 skeletal electron pairs and n boron atom octahedral, and from this one when we take out one, essentially one of this one we are taking out here, one of the axial position, and that leads to n minus 1 boron atoms having a nido structure. From this nido structure, okay, one can arrive at arachno structure by removing one more from this. This is taken out here. So, once you take out this one is taken out, you will be having a situation like this here, n minus 2 boron atoms. Okay. This for B4Cl4 tetrahedron looks like this one, okay, and also B9Cl9 tricap trigonal prism, okay, will have a structure like this. Okay, of course, you can see how it is made. So, this is a trigonal prism, okay, and you have to place 3 boron atoms and then connect them with these 4 to complete the structure like this. So, this is tricapped trigonal prism for vertices 9 or having 9 boron atoms, okay, and now you connect them with hydrogen atoms, okay, or if in this case it is chlorine. So, essentially you have terminal 9 BCl bonds or BH bonds. So, what would happen if we replace one or more boron atoms with main group elements? So, many such boron hydrides are known in which one or more boron atoms are being replaced by main group elements. So, these heteroborans may be classified by formally converting the heteroatoms, okay, to a BHX group having the same number of valence electrons. That means, we should remember now, for example, boron is coming from group 13 having S2P1 electronic configuration. In case of group 14 such as carbon, silicon, germanium and tin, we have S2P2 electronic configuration. That means, if one carbon is replacing boron, then that should replace one BH unit, because 4 electrons will be compensated. Similarly, if we are adding an heteroatom from group 15 having S2P3 electronic configuration, so that means in order to add one nitrogen, phosphorus or arsenic, we have to take out one BH2. Okay. In case of carbon, silicon, germanium or tin, we have to take out one BH, whereas in case of nitrogen, phosphorus and arsenic, we have to take out a BH2 unit, And in case of sulfur and selenium having s2p4 electronic configuration, we have 3 electrons more. As a result, we have to take out a BH3 unit to incorporate one sulfur or selenium. So, this we should remember. So, S2P1 is for boron. If you are replacing one boron and then if you are adding carbon, so one electron will be added. As a result, along with boron, one H also should be taken out. Similarly, in case of nitrogen, phosphorus, arsenic, when they are coming into the borane, so for each incorporation of each group 15 element, one BH2 unit has to be taken out. Similarly, for the incorporation of each element from group 16, one BH3 unit has to be taken out, so that the number of valence electrons remains same for the cluster formation. Okay. So, now 3 questions are there. Classify the following polyhedral heteroboranes according to their valence electron count. So, now basically if we just look into the first one, what we have is 2 carbon atoms are there along with boron. That means here vertices are 7, and in case of this one Sb9H11 vertices are 10, and in this one vertices are 12. Let us see what kind of polyhedral we can assign for these. Okay. And of course, we should remember here, okay, carbon, silicon, germanium and tin would replace one BH unit, whereas from group 15 they replace one BH2 unit, and in case of sulfur and selenium we have to take out one BH3 unit. Here one BH2 and here one BH3. So, C2 B7 H13. So, here you should remember if we have n boron atoms, n BH bonds will be there, for which we have to take out 2 electrons. So, essentially each boron atom is contributing 2 electrons towards making a BH covalent bond, and since we are counting all the electrons of hydrogen, for all practical purpose we can consider only 1 electron from boron towards cluster formation. So, in that case what happens, your carbon will be giving 2 electrons. So, 2 4 plus boron will be giving only 7 electrons, and then this will be 13. So, we have 24 electrons. So, that is 12 skeletal electron pair will be n plus 1, vertices will be closo, and if we have 10 vertices it will be nido, and if you have 9 vertices it will be arachno. So, since we have 7 plus 2 be 9, so it is arachno structure we have. Okay. So, this has an arachno structure, and now let us look into Sb9H11. So, in this case what we can do is we can consider 4 from sulfur and 9 from 9 boron atoms, and we have 11 here. So, it will be 24, will be 12 pairs. Okay. So, 12 pairs, this is n plus 1. Okay. If for this one, okay, 11 is closo, okay, and then if it is 10, this is nido. So, structure of this one will be nido. Okay. And similarly, we can consider this one C P B10 H11. So, in this one carbon is giving 2, phosphorus giving 3, plus we have 10 from this one and 11 from this one. So, we have 21 plus 5, 26. So, 26 electrons will be equivalent to 13 skeletal electron pairs. This is n plus 1, okay. And then if you have n, so and n should be 12, 12 n should be closo, and so we have here 10, 11, 12 we have. So, this has a closo structure. So, here 10, 11, 12. So, 12 vertices are occupied by 10 boron atoms, 1 phosphorus and carbon. So, it has a closo structure, and the structure will be icosahedron. Okay. So, this is how you can count and arrive at the structures of mixed boron hydrides. So, Wade's rule can also be applied to a wide range of other clusters of main group and transition metals. Okay. And then another thing is both BH and MCO3 moieties with C3V symmetry have 3 frontier orbitals with matching symmetries and the same number of electrons are available. So, that means for example, if we have B6H6 2 minus and Ru6 CO8 in 2 minus, we can consider both of them having similar structure. B6H6 2 minus is a n plus 1 skeletal electron pairs are there, 6 plus 6 12 plus 2 14 electrons are there. 14 electrons means essentially here I am counting 6 from boron, 6 from hydrogen, because I have deducted 12 electrons for BH bond formation. So, I am taking only 1 electron from boron. As a result, 6 plus 6 12 plus charge 14, 14 electron means 7 skeletal electron pairs, and if n plus 1 is 7, n should be 6. So, we have n 6 vertices are there, closure structure. Similarly, Ru6 CO12 2 minus is also a closure structure with octahedral cage, but how did we arrive at this structure? I will show you. Here you can see this is a C3V structure. If the C3V any molecule having a unit which has C3V structure, then that can be compared with one BH unit. So, that means essentially 3 electrons are coming from that one. Okay. So, here I have given for different groups the cluster fragment and the number of electrons coming towards the cluster formation. You can see MCO2 for group 6, okay, minus 2. Okay. That means you have to direct that many electrons, and group 7 minus 1 electron, or group 8 iron, ruthenium, osmium 0 electron, and group 9 cobalt, rhodium, iridium 1 electron comes. For MoCO3 0 contribution and 1 contribution from group 7, and 2 electrons should be considered from group 8 and 3 from group 9. Okay. Similarly, MCO4 units are there. We should have 2 electrons, 3 electrons, 4 electrons and 5 electrons. So, it goes like that. If we have a arene, eta 6 coordinated arene, we should consider 0 in case of group 6 elements, and 1 in case of manganese, technetium and rhenium, and in case of group 8 such as iron, ruthenium, osmium, we should consider 2 electrons for each such unit and 3 from here. Okay. So, and here we do some corrections, we cannot use directly. So, for that correction a formula is given here, x equals nu plus n minus 12, where x is number of cluster bonding electrons that are available. So, nu is essentially number of valence electrons from the metal atom, and n equals number of valence electrons provided by the ligand. So, let us look into at least one here, example RH4CO12, we shall see how many electrons are coming for cluster building, or okay, from each unit. Here RH4CO12 is there, we can think of each unit having RHCO3. So, okay. So, let me see whether we can arrive at this one. Okay. So, in case of RH4CO12, okay, we have rhodium. Of course, rhodium we have 7 plus 2, 9 electrons are coming. It is rhodium we have is D7S2, cobalt, rhodium, iridium. So, cobalt has D9, so 3D7S2, it is 4D7S2, okay, rhodium. So, we have 9 electrons are coming. So, equation given is x equals nu plus n minus 12. So, here essentially what we are getting is 9, and CO3 unit we have here 4 RHCO3 units. Okay. Each CO is giving 6 electrons and minus 12. Okay. So, essentially here it is, we have to consider how many electrons? We have to consider 3 electrons. If we consider 3 electrons for this one, so then we have essentially RH is 4 such units are there, 4 into 3, we have 12 electrons are there, and for this one 6 skeletal electron pair, which is equal to n plus 1. Okay. So, that means n vertices should be your closo, okay. And now n closo, that should be n should be 5, okay. This should be TBP, trigonal bipyramidal, and then here we have 4. So, n minus 1 vertices are there, n minus 1 rhodium atoms are there, it should be removal of 1. So, that means essentially we start with a closo structure of trigonal bipyramidal and remove one on this one, then we have a tetrahedral structure where each rhodium will be occupying these 4 corners with having 3 carbonyl groups on each one. Okay. So, that you can see here. So, you can see here. Okay. So, same thing is true in case of iridium 4 also. So, breaks into 4 MCO3 and each one will give 3 electrons towards cluster. So, essentially 12 electrons are coming, and 12 electrons I showed you how 12 electrons are coming, and 6 electron pairs totally, that is n plus 1. So, n equals 5 is closo, we do not have, we have one less. So, it is n minus 1 rhodium atoms we have, it has a nido structure. So, it has a nido structure, and this is how rhodium atoms are arranged in a tetrahedral fashion, and with each one having some bridging and all those things. So, the core structure can be determined using Wade's rules. Okay. And let us look into some of these anions here. Here germanium 4, tin 4, lead 4 are given, okay. And if you see here tricap triangular prismatic geometry we have, and in this one we have monocapped square antiprismatic geometry. In one of these case I would show you, for example, let us consider SN5 2 minus, okay. Simply I will consider SN5 2 minus, and let us try to predict the geometry of this one. So, in case of SN5 is from some carbon group what we have is S2 P2 electronic configuration. As I mentioned, 2 electrons you can simply take out for making SN bonds with the neighboring 2 SN atoms. So, we will consider only 2 electrons. If we are considering only 2 electrons, 2 into 5 will be 10 plus 2, 12 electrons are there. 12 electrons are there, and 6 is the skeletal electron pair, that is equal to n plus 1. Okay. So, now n will be 5, n equals 5 will be closo. So, it has a trigonal bipyramidal geometry. So, you can see here it has trigonal bipyramidal geometry. Same thing is true in case of PB 5 2 minus. So, this is how you can consider. So, that means essentially what you should do is just leave the S2 electrons for making 2 SN bonds and consider only the electrons that are coming from p orbital for the cluster building. Okay, that is a thumb rule. You can ignore the S electrons, consider only from the p orbital, no matter which group it belongs to. Okay, let us look into one more example here. Ge9 2 minus. Okay, germanium is also essentially coming below silicon. So, we are getting 2 electrons. So, 9 into 2 plus 2 charge equals 20 electrons. 20 electrons will be 10 skeletal electron pairs. This is n plus 1. Okay. So, if you have n, then this is closo. N vertices should be 9, that is n equals 9. So, we have 9. So, this should be a tricapped trigonal prismatic geometry. So, that we are arriving at the right structure. So, that you can use this one in this fashion to understand the structures. So, before I conclude, okay, let me give the uses of some of the group 13 elements. Okay. So, magnesium diboride is used in superconductors. So, magnesium diboride, that is MgBr2, is a cheap compound that has been known in the laboratory for over 50 years. In 2001, this simple compound was found to have superconducting properties. Jun Akimtsu and his co-workers discovered by chance that MgB2 okay, loses its electrical resistance when cooled, and MgB2 has a simple structure in which the boron atoms are arranged in graphite like planes with alternating layers of magnesium atoms. You recall I showed you that one. So, this is how it is there. Red one shows boron layer and the grey one shows the magnesium layer. So, alternately they are arranged, magnesium sheet and boron sheet, and with the composition of MgB2. Okay. And this high quality MgB2 can be synthesized by heating fine boron and magnesium powders together around 950 degrees centigrade under high pressure. So, thin films, wires and tapes have since been formed that have potential for applications in superconducting magnets, microwave communications and power applications. A new form of radiotherapy for brain tumors involves the irradiation of boron compounds with low energy neutrons. So, boron neutron capture therapy, also known as BNCT, it involves injecting the patient with a 10 boron labeled boron compound which preferentially binds to tumor cells, and when irradiated with neutrons, the 10 boron undergoes nuclear fission and produces a helium nucleus as shown below, okay, and 7 lithium plus nucleus, and liberates approximately 2.4 MeV of energy. So, here you can see this is the reaction that happens. The most promising boron containing compound for this application have been polyhedral boron hydrides having the composition such as Na2B12SH11SH or Na2B12H12. Okay. And boron carbide is also important and it is in use for in nanoparticles. So, these nanoparticles of boron carbide are introduced into a sample of the patient's own tumor cells, which are then injected back into the patient where they travel to the tumor and deliver the nanoparticles. The nanoparticles have also been coated with a peptide that improves cell uptake and labeled with a fluorescent dye that enables the nanoparticles to be tracked within the body. So, this is another important application, and of course, I have a couple of questions here, and predict the outcome of the following reactions. Okay. You can see here. Of course, here you should remember the relative strengths of the Lewis acidity of various boron halides, and here if you see BF3 NMe3 adduct, when it is reacted with BCl3, you can anticipate the replacement of BF3 by BCl3 simply because BCl3 is a stronger Lewis acid compared to BF3. So, reaction occurs here, and then in case of BCl3 NMe3, so this is already a strong adduct, BF3 being a weaker Lewis acid compared to BCl3, there is no reaction. In this case again, NMe3 being a stronger Lewis base compared to SME2 replaces and SME2 comes out, whereas in this one SME2 is a weaker Lewis base compared to NMe3, there will be no reaction. So, essentially you can see in first case reaction occurs, in second case no reaction, here reaction occurs and here no reaction. Okay. And borosine reacts with 3 equivalents of HCl to give a material of composition B3N3H9Cl3. So, write the structure of the compound and how does it react with HCl. So, you should remember in borosine, okay, BN bonds are polarized with boron carrying plus charge and nitrogen carrying negative charge like this I have shown here. Okay. And then, so that means once you polarize, you can notice where exactly Cl will be going and where H will be going. So, since B plus is there, Cl minus will be coming, and N plus is there, H will be, N has lone pair. So, H will be coming here and you form a compound of this type. So, this is the product of the reaction of borosine with HCl. Okay. You can see here, you can see, okay, charge is here. So, automatically you know where HCl is there and it goes and you get that product. So, in this one you can also write the product here in the reaction I showed here, we should be able to write the product. Okay. So, let me complete these reactions. So, BCl3 plus 3 ETOH will give BOET thrice plus 3 HCl, yeah, BF3 plus ETOH gives adduct, there is no nucleophilic substitution, it gives only the adduct, okay, and BCl3 plus 3 PHNH2 gives BNHPH. So, again nucleophilic substitution plus 3 HCl comes out, and BF3 plus KF gives KbF4. It is a ionic salt. So, we should be able to do that one, okay. Or in these cases, if we can also add a base, so that if you add triethylamine hydrochloride precipitates, reaction will be much faster, okay. So, last question, BCl3 is a volatile liquid, suggest a way in which it can be more conveniently handled. So, if it is liquid and it is volatile, it is more reactive, it is very difficult to handle. What we can do is, we can make an adduct, okay, with for example, SMB2, we should make an adduct in such a way that we should not use a stronger Lewis base. For example, we can make an adduct with dimethyl sulfide, and an adduct of dimethyl sulfide is a crystalline solid which is very easy to handle, and it is less sensitive towards hydrolysis than BCl3, so that we can handle weighing, all those things we can do it easily, okay. Although F is more electronegative than Cl, why BCl3 is stronger Lewis acid than BF3, I already discussed with you. So, there is no need to repeat the answer for this one again. So, let me summarize the chemistry what we learned about group 13 elements. Except for boron, other elements such as aluminum to thallium have low electronegativity value and all are metals, okay. +3 acetate dominates the chemistry of group 13 elements. Inert pair effect appears for the first time among p block elements. The +1 acetate for thallium is moderately stable. So, I did not give much emphasis to explain inert pair when I was discussing group 13 elements. However, I will explain you in detail the inert pair effect when I start the chemistry of group 14 elements as well as group 15 elements. So, boron forms a large number of neutral and ionic boron hydride clusters as a result of its electron deficiency. All boron trihalides are very strong Lewis acids, and NaBH4 sodium borohydride and lithium aluminum hydride find application as very useful reducing agents in inorganic as well as organic synthesis. So, with this one, okay, I am concluding the chemistry of group 13 elements. Have a nice time reading inorganic chemistry. Thank you.